Hi everyone, this is Kalyan Kumar and welcome to another edition of Atomic Structure videos. Welcome to my channel Chemistry Tutorials, and today we're going to talk about part 4 of 13 of Atomic Structure. In the last part we talked about the plum pudding model of J.J. Thomson and how J.J. Thomson had discovered electron, and he was more emphatic in trying to put the electron and fit it inside an atom. And the best way to do it was to keep the electron stationary, spread all over in a jelly of positive charge. And his model was called the plum pudding model. So now let's understand what Rutherford's model is and what made Rutherford make some changes in J.J. Thomson's model. So we're going to talk about the Rutherford's model, and these are the three important people in this: Ernest Rutherford, Hans Geiger, and Ernest Marsden. And by the way, this Hans Geiger is the same guy who created the Geiger-Müller counter for measuring radioactivity. Now in 1909, now remember 1904 was the time when J.J. Thomson published his paper of the model of an atom. 5 years later, in 1909, Ernest Rutherford, and surprisingly and interestingly, in fact, he was a former student of J.J. Thomson, directed the most famous Geiger-marsdon experiment. An experiment which was actually attributed to Rutherford, but Rutherford never performed the experiment. It was his students Geiger and Marsden who performed the experiment, based on which he arrived at certain conclusions, which now is known as the Rutherford's model. Now, initially, he chose Hans Geiger to assist him in bombarding a thin metal sheet with high-energy alpha particles that were being emitted by a radioactive source. So he wanted to have a metal sheet and bombard the metal sheet with alpha particles. And alpha particles, of course, they were called alpha particles because nobody knew what they were actually. So they were just called alpha particles, and they were being emitted by a radioactive source. Now they chose gold as the metal, since gold is highly malleable and ductile, so you could convert them into sheets or wires or whatever you wanted. The next problem was to devise a screen that would fluoresce when these alpha particles hit it. Geiger and Rutherford devised a screen that was coated with zinc sulfide. It produced sparks called scintillations when alpha particles struck its surface. So whenever a charged particle, in fact, of course, they did it for alpha particles, but whenever a charged particle strikes a surface coated with zinc sulfide, it produces sparks. It is similar to the phosphorescent material used by Thomson in calculating his E by M ratio for electrons. Now often, interestingly, Geiger would be left in a darkened room to count the scintillations, and which was an essential part of the experiment. In the experiment, Rutherford directed Geiger to find out the deflection angle of the alpha particles after passing through the gold foil. So basically, Rutherford has his own reservations about the fact that the atom is electrically neutral because there's a soup of positive charge and electrons are all spread over equally. He wanted to know for sure whether that was true. So what he did was, he was bombarding alpha particles on a gold foil, and he wanted Geiger to count the scintillations and notice whether there are any deflections. If there are no deflections, it would simply mean the atom is homogeneous. On Geiger's request, because this was going to be very taxing, on Geiger's request, Ernest Marsden, another student of Rutherford, was roped in to exactly observe the range of deflection angle and the number of such deflections. Marsden noted that the majority of alpha particles passed without deflection, while some showed small deflections. However, 1 in over 20,000 particles suffered a deflection of more than 90 degrees. So that means 1 in 20,000 alpha particles had a deflection that was behind the gold foil. So they struck the gold foil and went back. It does not necessarily mean they went back on the same path, but they definitely had a deflection of more than 90 degrees. So they were hitting the screen behind the gold foil after striking it. So it is to be expected that there could be 1 or perhaps 1 in over 100,000 particles which could have gone back in the same direction, because even those deflections of more than 90 degrees were many. So there were many deflections of more than 90, 110, 120, 130. So from that logic, it is to be expected that there could be deflections even at 180. So alpha particles could go back the way they come. Of course, there was no way of proving this. Now, this was, remember, the entire thing was happening in 1909, and 2 years later in 1911, Rutherford, it took him 2 years to analyze all these experimental data, and then he presented his analysis of the observations, leading to what is now known as the Rutherford's atomic model. Now let's understand what was the Geiger-Marsdon experiment based on which all these conclusions were drawn. And then of course we'll have a look at what these conclusions were. So the Geiger-Marsdon experiment looks something like this. There is this thin gold foil, which is 5 into 10 to the power minus 7 meters thick. Now God knows how they actually made this, but remember this thickness is even thinner than a human hair. So we really don't know how they made this, but they actually did it. 5 into 10 to the power minus 7 meters thick, and the purpose of it was that they wanted a gold foil which was so thin that it could be assumed to be just 1 atom thick. Now they had a circular screen, and this screen was coated with zinc sulfide. The circular screen because you wanted to note the deflection that was happening behind the gold foil also. There was this container coated with lead. That was because there are some alpha particle source inside, radioactive source, which was polonium-214. And the path of the alpha particles was this. And this is how they were supposed to hit the screen. Now, if we assume that the Thomson's model was correct, which means the atoms are homogeneous, it would mean that the alpha particles would simply travel in a straight line. They cannot be deflected because the atom is homogeneous. So whatever deflection it would suffer from one part of the atom, that would be supported by the other part, and therefore there will be no effective deflection. And since the positive charge was homogeneously distributed, that you cannot expect a high momentum alpha particle to be deflected by a diffused kind of a positive charge. So the experimental observation was expected to be like this. Alpha particles go, hit the screen, and they flash, and they are flashing right in the same path in which they're traveling, no deflections happening. This is what is expected if the Thomson's model of the atom was correct. Now let's understand the Thomson's atom model. Now, according to Thomson's model, atom looks like this. And why do alpha particles are expected to travel in a straight line is because it is totally homogeneous. Everywhere the charges are equal, and therefore the alpha particles are expected to simply pass through. No deflection happening, they're simply expected to pass through. And this is exactly what is expected if Thomson's model was correct. Now let's understand what was the actual observation. The actual observation was like this. Most of the alpha particles simply went through straight, but there were a few which suffered deflections on either side. The deflections were equal on either side. Some deflections were greater in angle, and some deflections were even greater than 90 degrees. Look at that, more than 90 degrees. And one is expected to go back at least, because if you can have angles greater than 90 at 110, 130, 150, then 180 is expected. But remember, there's no proof for that because there's no coating at the back. So based on this observation, what was Rutherford's model? The Rutherford's model, based on these results, was the following. He said, since more than 90% of the alpha particles went straight through the gold foil, it suggested that most of the atom is empty space. So he says most of the atom is empty space since most of the alpha particles simply went through, but there were deflections. And these deflections were happening on alpha particles that were traveling almost close to the speed of light. And therefore he said the entire positive charge is concentrated at one point. And since the deflections were equal on either side, he expected the positive charge to be right at the center of the atom. He said if all the positive charge is concentrated in a very small volume, only then the charge density, the positive charge density will be so high that would be able to deflect the alpha particles by angles sometimes even greater than 90 degrees. So, since alpha particles were traveling with the speed of approximately 1 × 10⁷ meter per second, they carried a great amount of momentum. Such a particle could only be deflected if it is assumed that all the positive charge of the atom is concentrated in a very small volume inside an atom. And this was called the central charge region. Later this was named the nucleus. And this extract is from his own paper, which said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell, that is a bullet, at a piece of tissue paper and it came back and hit you. On consideration, I realized that this scattering backward must be the result of a single collision, and when I made calculations, I saw that it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute central core. It was then that I had the idea of an atom with a minute, massive center carrying charge." And the reason he talked about mass was simply because if the entire mass is not concentrated in the nucleus, then this high momentum alpha particle could dislodge the nucleus itself. And you never find that happening. You never find that the gold foil has suddenly become ionized, that the positive charge has gone away. So it means that the mass of the nucleus is so high that it is able to withstand the impact of the alpha particle and not move because it's massive. It has large mass, which means almost the entire mass is concentrated right at the center. Now Rutherford calculated the approximate diameter of the nucleus to be about 1/4,000 times that of the gold atom, which is now believed to be 1/20,000 times that of its atom. So to give you a perspective, just imagine that the earth is an atom and a small piece of marble would be the nucleus. That is the size difference between the marble and the earth, 1/20,000 times. Now, and since the high-speed alpha particles were not able to dislodge the nucleus of the atom, it implied that almost the entire mass of the atom was located in the nucleus itself. Though neutrons had not been discovered yet, Rutherford did of course predict the existence of neutral particles with mass, and he was the one who discovered protons in 1920, for which of course he also received the Nobel Prize. Rutherford did not make the connection between the central charge and atomic number. Now, just after a month after his paper was published, the proposal regarding the exact identity of atomic number and the nuclear charge was made by Antonius van den Broek and later confirmed experimentally within 2 years by Henry Moseley. Now let's understand, how could Rutherford's model explain the experiment that Rutherford saw? So this is the Rutherford's model. Right at the center, small gray matter, that is the nucleus. So alpha particles come, and as long as they pass safely at a distance from the nucleus, they simply pass through. And as you can see, 90% of the alpha particles are going to pass through because most of the atom is empty space. But when an alpha particles come pretty close and hits the nucleus, it's going to get deflected. And it all depends upon at which angle it comes and hits it. Most of them are going to pass through, but some are getting deflected on either side, and most of them still pass through. And some of them, perhaps one in many, would come and hit right at 180 degrees and go away, and some can suffer multiple deflections, 1, 2. So all these were expected. So this is only possible if the Rutherford's model is correct. But remember, Thomson concentrated his entire model based on the fact that he had discovered electron. He wanted to place the electron inside an atom. Rutherford, on the other hand, had discovered nucleus, and he didn't really care about where the electrons were and what they were doing. He wanted the atom to have the nucleus at the center because his experiment suggested that. He had no clue on how to place the electrons. So the Rutherford's model served to concentrate a great deal of the atom's charge and mass to a very small core, but didn't attribute any structure to the remaining electrons. It did mention the atomic model of Hantaro Nagaoka, in which the electrons are arranged in one or more rings with the specific metaphorical structure of the stable rings of Saturn. So he said electrons were moving in Saturn-like rings, and that is why whenever we talk about an atom, we generally get a picture like this, in which the electrons are moving, and they're all moving in different planes. Sometimes you might see they might collide, but they will not collide because they're all moving in different planes. So this is how an atom is expected. But of course, later on we come to realize that even this structure doesn't work. But remember, every structure gave us something that the next structure used and improved upon. So every structure is as important as the other. And this is how science progresses. So that is the end of this video that talks about the Rutherford's model. In the next episode, we're going to be talking about nature of radiation. We'll talk about what is electromagnetic radiation. We'll talk about Maxwell's theory, what Maxwell did and what he predicted, and what were his observations. So we're going to talk about nature of radiation in the next episode. So if you have any comments, suggestions, any queries, doubts, any questions that you have, any suggestions, please drop them in the comment section below. If you haven't subscribed to this channel, please do so immediately, as you're going to get lots and lots of videos of this kind, and you will find the entire atomic structure series and all the lessons of grade 11 and 12 in this particular channel. So if you haven't hit the subscribe button yet, do subscribe quickly so that you can get the right notification at the right time the moment I post any video. If you like this video, please also hit the like button. It is an encouragement that makes channels like mine grow and makes me confident enough and motivates me to make more and more videos like this. This is Kalyan Kumar. Have a great day and thank you for watching.